Okay, welcome back. What I want to look at today is impedance matching. Now, when we talk about impedance matching, we're looking at impedance matching in regards to the power from an amplifier to feed, let's say, for argument's sake, a speaker. So you could be looking at impedance matching to get the output from an amplifier that will feed your music through your speaker box. Okay, so that's what we're looking at when we talk about impedance matching. Now, you need to do additional reading in regards to impedance matching so that you get a wider concept as to what we're trying to talk about here. I'm only giving you an example or a brief illustration as to what impedance matching is about, because it can become very, very complicated. Okay, so the term impedance matching is rather straightforward. It's simply defined as the process of making one impedance look like another. So you're trying to make the impedance of your amplifier look like the impedance of your speaker. Frequently, it becomes necessary to match a load impedance to the source or internal impedance of a driving source. Okay. Now, a wide variety of components and circuits can be used for impedance matching. This series summarizes the most common impedance matching techniques. Okay. Now, only some, okay, not all. The impedance matching techniques are varied and I'm sure have been modified over the years with modifications and with new methods of applying impedance matching. Okay. Now, the reason and concept of impedance matching. The maximum power transfer theorem says that to transfer the maximum amount of power from a source to a load, the load impedance should match the source impedance. Should match the source impedance. In the basic circuit, the source may be DC or AC, and its internal resistance Ri, that's resistance internal, or generator output impedance Zg. Now please note Zg is the generator impedance, drive the load resistance RL. Now notice that in DC you will meet resistance, and in the generator you will meet impedance. Okay. That will be specific to DC, and because you're using a generator, the impedance will be it's AC. Now again, do some additional reading for yourselves. Okay. And all I've done here is give you a formula. Okay. RL equals Ri or ZL equals Zg, and I've said here RL equals DC resistance, ZL equals Zg generator impedance. Okay. Let's complete a little bit more so we can see it all. Okay. And here, this diagram shows you internal or output impedance, AC or DC source, okay, the load RL or ZL. Now remember, the load will still be resistive, but it is the impedance that will occur in this circuit here at this point. Okay, but you'll still be driving the load, and that will still be seen as a impedance or as a resistor. resistance which opposes the flow of current. Okay? And here we have RL equals RI, or ZL equals ZG for maximum power transfer. Okay? Now maximum power is transferred from a source to a load when the load resistance equals the internal resistance of the source, as we mentioned earlier. Okay? Now a plot of load power versus load resistance reveals that matching load and source impedances will achieve maximum power. And this simply shows you here in figure 2 maximum power in watts against RL equals RI resistive load, and you can see that maximum power 50% efficiency. Now obviously we need the percentage to be more effective than that. 50% doesn't really give us, it's not indicating maximum power transfer, but probably in this case it is. Okay? Load resistance, and remember this is only an example. Right? Now by varying the load resistance on a source shows that maximum power to the load is achieved by matching load and source impedances. At this time efficiency is 50%. But we need it to be more efficient than that. We need to be looking at least 90–95% efficiency, if not even better. Okay? But again, do some additional reading, as I'm only providing the grounding in regards to impedance matching. So do some additional reading. A key factor of this theorem is that when the load matches the source, the amount of power delivered to the load is the same as the power dissipated in the source. Therefore, transfer of maximum power is only 50% efficient. So here you can see that the reason why we have 50% efficiency is because half the power is being dissipated in the load, in the source internal resistance. Okay, so because half the power is dissipated in the source, we only get half the power out, which is not what we want. We want a much better ratio than that. The source must be able to dissipate this power. To deliver maximum power to the load, the generator has to develop twice the desired output power, and that's what will need to be done. Now applications. Delivery of maximum power from a source to a load occurs frequently in electronic design. One example is when the speaker in an audio system receives a signal from a power amplifier. Now, maximum power is delivered when the speaker impedance matches the output impedance of the power amplifier. Okay. Now, while this is theoretically correct, it turns out that the best arrangement is for the power amplifier impedance to be less than the speaker impedance. The reason for this is the complex nature of the speaker as a load and its mechanical response. Now, because the speaker operates as a diaphragm system, its movements, if you make the speaker move too fast, you will cause it to burst. Its its diaphragm. The diaphragm will burst. So you have to allow the speaker to move at a response rate that does not damage the speaker itself. Okay, and that is what you need to bear in mind. Again, do some additional reading in regard to speakers and their oscillation. And here we have the audio amplifier, power amplifier. ZG, this is your source, okay? And here we have the internal resistance of our power amplifier as 1 ohm, okay? And that's your speaker output, which we've put at 8 ohms. And if you look back at what we've just said, if we make the source resistance lower, we get a better output percentage. Now again, remember, to understand some of these, you have to draw the diagrams them out yourselves. Don't just take it as read from the screen, okay? Right, here we have an unmatched impedance to provide the best amplifier and speaker performance as shown in figure 3. Now you can see here that the source is 1 ohms, okay, and we've got the speaker at 8 ohms. This will now give us more efficiency so we can get the maximum output power to our speaker. Now, another example involves power transfer from one stage to another in a transmitter, figure 4. The complex R plus or minus JX. Now, if you look at one of my videos, you'll see that I speak about J notation and I do some calculations on J notation. So again, you need to do some additional reading for yourselves and some mathematical application of J notations. Input impedance. So again, coming back to this, the complex R plus or minus JX input impedance of amplifier B should be matched to the complex output impedance of amplifier A. Okay. Now it is crucial that the reactive components cancel each other. One other example is the delivery of maximum power to an antenna. Figure 5. Here the antenna impedance matches transmitter output impedance. Okay. Now the reactive components cancel. Now we got inductive reactance and we can get capacitive reactance. Okay. Okay. Let's make sure we have it all in. Let me just go back a little bit. Make sure we get it all in. Okay. 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 Just making sure that it's all in shot and I haven't missed anything out or cut anything off. Okay. And here is our amplifier A and amplifier B. All we're doing here is using one first stage amplifier, second stage amplifier. So we amplify it here, then we amplify it here again. But be aware that when you amplify your second stage, because you will need some kind of feedback to control the output. Because remember, these would be operated or represent operational amplifiers, and op amps has almost an infinite gain. Okay, so you'll need some means to control and acting as feedback to control the output. And that's your inductive reactance and your capacitive reactance. Okay. Now, figure 4 impedances in radio frequency transmitters must be matched to pass maximum power from stage to stage. Most impedances include inductances and capacitances that must also be factored into the matching process. And here we have, all we're looking at here now is an antenna, okay, an antenna for your radio. I mean, take your car for instance. Your car has an antenna. Sorry about that. Okay, but you can see transmitter output amplifier here, stage 50 ohms. The antenna out resistive load is also 50 ohms. So there's no reason why you should not get maximum transfer to here. But again, what would be the effect if we was to reduce the transmitter amplifier and reduce it in resistance? Let's go say 20 down to 20 ohms. That may well again give us more power to this antenna, but we'll take it as it stands for now. I'm just speaking off the top of my head, but again, do some additional research, do some reading, get familiar with that for yourselves. Okay, it's not very difficult. All you have to do is type it in on transmitter output amplifiers on Google, and that will do you fine. Now, figure 5, antenna impedance must equal the transmitter output impedance to receive maximum power. That's all we're saying here now. Okay, transmission line matching. This last example emphasizes another reason why impedance matching is essential. The transmitter output is usually connected to the antenna via a transmission line, which is typically coaxial cable. Excuse me. Now, in other applications, the transmission line may be a twisted pair or some other medium. A cable becomes a transmission line when it has a length greater than λ/8 at the operating frequency, where λ equals 300/f in megahertz. This means λ equals 300 divided by f, the frequency. Okay. And for example here, can I make this bigger? No, okay, you should be able to get that there fully. We'll come back a little bit, make sure we can get it all in. But we should be able to see that. So you can see here, for example, the wavelength of a 433 megahertz frequency is λ equals 300/f megahertz. Typically equals to 300/433 equals 0.7 meters, or 27.5 inches. Now if you put this into your calculator, you'll find that it should come out to 0.7 meters. Now a connecting cable is a transmission line if it's longer than 0.7/8 equals 0.0875 meters, or 3.4 to 4 inches. All transmission lines have a characteristic impedance, Z0. That's a function of the line's inductance and capacitance. Okay, so to find Z0, you have to determine the square root of L/C. Again, do some additional reading here for yourselves. Okay, I'm only giving you a brief outline. To achieve maximum power transfer over a transmission line, the line impedance must also match the source and load impedances. If the impedances aren't matched, maximum power will not be delivered. In addition, standing waves will develop along the line. This means the load doesn't absorb all of the power sent down the line, meaning that you have a power loss down the line created by additional waves, which in turn takes up its own form of energy. Okay. And that is where twisted paste cables will come into its own to eliminate some of this wave. Now here, all I'm doing here now is just showing you that source, generating impedance, coax the cable, ZG equals Z0 equals ZL, okay, and that would be your coax line, and ZL for your acting as your transmission line. Now figure 6. Transmission lines have a characteristics. Impedance Z0 that must match the load to ensure maximum power transfer and withstand loss to standing waves. Okay. Make sure we have that in. Okay. Now, consequently, some of the power is reflected back toward the source and is effectively lost. The reflected power could even damage the source. Standing waves are the distributed patterns of voltage and current along the line. Voltage and current are constant for a match line, but vary considerably if impedances do not match. Okay, so by having a match impedance, you help to reduce these waves, which will be a loss of power. Okay. Now, the amount of power lost due to reflection is a function of the reflection coefficient. I call that inverted L. Okay, just for my means, I'm sure there's a name for this symbol, and I'm sure you guys can look it up for yourselves. Okay, but for me, I'll just refer to it as an inverted L. Okay, and the standing wave ratio, or R if you want. Now, these are determined by the amount of mismatch between the source and load impedances. The SWR is a function of the load ZL and line Z0 impedances. SWR equals ZL over Z0 for ZL which is greater than Z0. SWR equals Z0 over ZL for Z0 which is still greater than ZL. Okay. For a perfect match, SWR equals 1, assume ZL equals 75 ohms and Z0 equals 50 ohms. And here you will have your standing ratio, 75 over 50 giving you 1.5. Now the reflection coefficient is another measure of the proper match. Okay, so if you want to know if something of your cables match each other from power to source, or power to load, I should say, from source to your load, then this is another way of doing that. The reflection coefficient is another measure of the proper match. Inverted L for me equals ZL minus Z0 divided by ZL plus Z0. Okay. That almost reminds me of the product over sum ratio for calculating resistors in parallel. For a perfect match, inverted L will be 0. You can also compute inverted L from the SW value. Okay. And this just shows you that process here. Again, you need to do some additional reading for yourselves and some additional research. Again, remember for yourself, knowledge is power. Okay, so acquire that skill. Calculating the above example. Okay, and here I've simply put it down here for you. Okay, and 0.5 over 2.5 equals 0.2. Okay. Now I must admit here, I can't recall if it's a ratio or a unit, so do forgive me for this. But that's no point not putting a unit or specifying if it's a ratio. But again, as you do a bit of reading, you will then be able to be more precise. So I've got to leave you something to do, haven't I? I can't do it all for you. Now, looking at the amount of power reflected for given values of SWR, it should be noted that an SWR of 2 or less is adequate for many applications. An SWR of 2 means that reflected power is 10%, therefore 90% of the power will reach the load. Okay? Now that's better, isn't it? I mean, that is brilliant. So if we look at an SWR of about 1.5, we can almost be sure that we're getting at least 98% of our power to the load. And that's brilliant, considering that we are transmitting it over cables which may well have their own capacitive effect. This table just shows you, let me just get the table in full, okay, bear with me for a second. Okay, and you can see here reflected power, okay, against standing wave ratio. So I'll be looking at here how, as we can minimize the wave ratio, then we can get more power out, okay. So our power goes up as we can reduce the standing wave ratio, okay, becomes more efficient. That's all this graph is trying to tell you here. Okay. So make sure I can get it on. Step back a bit. And here, what I've done here now is I've just given you find the frequency of a wave with wavelength 2.5 meters and speed 50 meters per second. And all I've done here is to show you how this has been done. Okay, frequency F, wave speaker, wave speed, wavelength, lambda, okay, etc. And again, you need to do a few of these for yourselves. You can find these in any good electrical principles textbooks, or simply go online and type in wave calculation of wavelengths, okay, and it brings it up. Use Google, I would suggest, because that gives you a wider span of data and information. Okay. Okay, I would say thank you for now, and look forward to speaking with you again in due course. Take care for now. Bye bye.